Welcome back, Calculus friends. This is AP Calculus Section 5.4, Day 2 notes. So today we are going to continue talking about the fundamental theorem of calculus and this idea that if we have a given function and we find the integral of that and then we differentiate that result, we get back to the function that we started with, right? That relationship between differential calculus and integral calculus, and that these are inverse processes. So the fundamental theorem of calculus, part 1, we were talking about yesterday. It says, suppose f is continuous on the closed interval from a to b. If g of x is the integral from a to x of f of t dt, then the derivative of g, or g prime of x, is just equal to the function f of x. And then the fundamental theorem of calculus part 2 is actually the evaluation theorem, which we're already familiar with, that the integral from a to b of f of x dx is equal to that function integrated and evaluated at b minus that function integrated and evaluated at a, where f is any antiderivative of the original function, that is, capital F prime is equal to little f, basically saying that the constant term doesn't matter because when we integrate and get a plus c, but then when we differentiate, the derivative of a constant term goes away, so it doesn't matter what that constant term was. All right, so example 1 is asking us to use the fundamental theorem of calculus part 1 to find the derivative of the function. So we are given that g of x is equal to the integral from 1 to x of 1 over t cubed plus 1 dt. And it doesn't really matter what our lower limit of integration is. It only matters what our upper limit of integration is, and the fact that it is x, because, again, we know that when we integrate and then differentiate, basically we just get back that original function. So basically, by the fundamental theorem of calculus, g prime of x is going to be equal to the derivative with respect to x of this integral from 1 to x of 1 over t cubed plus 1 dt. And basically that just means that we end up with 1 over x cubed plus 1 as our derivative of our integral. Example 2 is very similar. Here, notice that my lower limit of integration is 3, not 1. And again, as I said in the last problem, it doesn't matter what the lower limit of integration is because as long as x is our upper limit of integration, we basically just get back the function that we started with when we differentiate our integral. So once again, g prime of x is going to be the derivative with respect to x of the integral from 1 to x from 3 to x of e to the t squared minus t dt. And once again, this just gives us back e to the x squared minus x as our derivative of our integral. Example number 3 has a little bit of a catch to it. Notice that our limits of integration look a little bit different here, right? Notice that we have switched it up, and instead of going from a number to x, now we are going from x to a number. So if you recall our notes from yesterday when we looked at some of the properties of the definite integral, one of our properties of the definite integral from yesterday was that the integral from a to b of f of x dx is equal to the opposite of the integral from b to a of f of x dx. And so that property is what we need for this problem. So basically that just tells us that we are going to get the opposite of the integral, or the function basically that we are integrating. So we end up with our f prime of x being equal to, since capital F was our original function, our f prime of x is equal to the opposite of the derivative with respect to x of the square root of 1 plus secant t dt. which in this case is just going to be negative square root of 1 plus secant x. Just need that negative sign in front because we flip-flopped our limits of integration. Example number 4 is perhaps the most interesting because we're going to use the fundamental theorem of calculus part 1 just like we have been doing, but notice that now we are going from 0 to x squared. So this problem is going to require us to use the chain rule. Okay, so our function h of x is given as the integral from 0 to x squared of the square root of 1 plus r cubed dr. Okay, so I am going to start by saying, let's let u be x squared. Okay? So then my function becomes h of u because I have changed my limits of integration to be in terms of u. So now it's from 0 to u instead of from 0 to x squared. The square root of 1 plus r cubed dr does not change, right? Just my limits of integration. But my h prime of u now is going to be equal to the derivative with respect to u of the integral from 0 to u of 1 plus r cubed dr. But again, chain rule says we have to multiply by the derivative of u with respect to x. That is the chain rule part. So what we get is we get the square root of 1 plus u cubed du, which is going to be equal to the square root of 1 plus x squared cubed times, then we need the derivative of x squared, which is 2x. So I would write this as 2x times the square root of 1 plus x squared cubed is x to the 6th. So if your limits of integration involve a function other than just x, because the derivative of x is 1, right? But the derivative of something that is not x is not going to be 1, then that's going to require you to do a u substitution and do chain rule to calculate the derivative of the function. Our last example today has multiple parts. Example 5 says, let g of x be the integral from 0 to x of f of t dt, where f is the function whose graph is shown. Okay, so right now, I want to make a little note here on the side, just so that we're thinking about this correctly. G of x is the integral of f of x. So f of x, then, is the derivative of g of x, right? Keeping in mind that integration and differentiation are inverse functions or are inverse operations that undo each other. So my first question asks, at what values of x do the local maximum and minimum values of g occur? Okay, so again, if we are looking at the function f, and the function f here is the derivative of g of x, well then keep in mind that the local maxes and mins on a derivative appear to be x-intercepts, right? It's been a while since we've talked about this. So where does my graph cross the x-axis? Well, that happens in multiple places. So I would say x equals 2, 4, 6, 8, and 10. Oh, sorry, just 2, 4, 6, and 8 are local max and min values of g of x. I'm going to talk about 10 in just a moment. Okay, and why is this? This is because f of x changes from positive to negative or negative to positive. right? So anytime our graph crosses the x-axis, changing from positive to negative or negative to positive, that is a location where we know that function's integral or antiderivative had a local maximum or a local minimum value. Okay, and you may be wondering right now, why did I not include x equals 0 and x equals 10? Okay, well, again, this goes back to our definition of local maxes and mins. So let's see if I can squeeze this in here. So note, x equals 0, x equals 10 can't be called local max or min values by definition because we can't see both sides. Remember, endpoints of an interval can only be absolute maxes and mins. They cannot be local maxes and mins. Okay? So the next question is, where does g attain its absolute maximum value? Okay, well, remember, g of x is the integral, right, or is the area under the curve of the graph that we are looking at. So the question is, where would the area under the curve be the greatest? Well, if you look at it, keeping in mind that any area above the curve is positive and any area below the curve is negative. So cumulatively speaking, g of x is going to have its maximum value at x equals 2. Because the area under the curve is greatest at this point. Okay. And then part C is asking us, on what intervals is g concave downward? Okay, well, again, what is the relationship between concave downward and increasing decreasing? Well, g of x, let's write this down, is concave down where f of x is decreasing. Because remember, f of x is the integral, right? Or g of x is the integral of f of x. Okay? All right, so where is this taking place? Well, from 1 to 3, our graph is decreasing. And then from 5 to 7, our graph is decreasing. And again, from 9 to 10, our graph is decreasing. And then finally, part D is asking us to sketch the graph of G. And we just did this, a similar problem, in our last section of notes here. All right, so remember how we did in our last section of notes. Let's write this down again. The y values on f of x are the slopes on g of x. Okay, so we are going to create a slope field. And then the other thing is the accumulated areas on f of x are points on g of x. So we're going to figure out, we're going to estimate what some of those accumulated areas are so that we can do a good job of figuring that out, okay? So first, why don't we go ahead and create our slope field. So I'm going to make a coordinate plane. And I'm going to use the same values on my x-axis and on my y-axis that my function f, whose graph was shown, had. So I will go from like 0 to 10 on the x-axis. And I will go from like 0 to 0.6 on the y-axis. Okay. All right, so beginning with the y values on f of x are the slopes on g of x. So just looking at my graph, at x equals 0, the y value of the given graph, for example 5, was 0. So my slope is going to be 0 at x equals 0. At x equals 1, my y value is 0.6. So I want to try to make a slope that looks like 0.6, right? Well, remember, 0.6 is really quite high here on my scale. So 0.6 on this particular graph is going to look like a fairly steep slope. 0.6 is going to look like this. When x is 2, the value of my curve is 0. So I have a 0 slope again at x equals 2. At x equals 3, it looks like my y value is maybe about negative 0.3 perhaps. So something like this. When x is 4, my y value is 0. So 0 slope. When x is 5, my y value appears to be 0.1, so a slightly positive slope. When x is 6, my y value is 0. 0 slope again. When x is 7, my y value is negative 0.1 again. When x is 8, my y value is 0. When x is 9, my y value is positive 0.1. And then finally, when x is 10, I am back to 0. Okay, so I have a great slope field drawn here. So now I need to consider my accumulated areas, and this is going to require me to do just a little bit of estimating. So if I go back here and I look at the graph that was given for this problem, right here. Sorry for the mess on the rest of the page, but again, I'm just going to try to sort of chop this up into some shapes that I can estimate the areas of. I'm not trying to be perfect here. I'm just trying to get a guess at what my accumulated areas are going to be. So I'm going to kind of look at this as a triangle here, and this as a triangle here, and this is a triangle and a triangle, and I'm just going to kind of chop up my areas, so to speak. so that I can sort of calculate what's going on here. And remember that the areas of triangles are 1/2 times the base times the height. So when I'm looking at the cumulative area from 0 to 1, my base is 1, my height is 0.6, so 1 times 0.6 times 1/2 would be 0.3. So I'm just going to write these down first. Obviously, g of 0 is 0. G of 1 is going to be approximately 0.3. Then I go back and look at my graph again. G of 2, well, I have another triangle that's symmetrical to the one I just found, so I know that's going to be another 0.3, right? So G of 2 is going to be approximately 0.3 plus 0.3, which is 0.6. G of 3, I'm going to have my cumulative area of 0.6 plus, now I look at my graph, and again, so I'm adding these areas here, right? Well, now I'm going to have to subtract because I'm going below the x-axis, and that triangle appears to have a base of 1 and a height of about negative 0.3, and then times 1/2, so that's going to be subtracting off about 1.5, or 0.15. Okay, so that's going to be approximately 0.45. G of 4 then, I have my 0.45, and again, what am I adding to it? Go back to my graph. Well, I'm adding another negative 0.15. So now 0.45 plus a negative 0.15 is going to put me at about 0.3. Keep going. G of 5 is approximately equal to the cumulative area plus what's next. Well, let's see what triangle's next. Now I jump above. And again, this is like 0.1 high times 1 times 1/2. So basically 0.05 positive. So this is going to be 0.35. G of 6 then is going to be that 0.35 plus, what am I adding? Oh, I'm adding another triangle that I just added before. So that's going to be another 0.05. So now I'm at approximately 0.4. G of 7 is going to be 0.4 plus, what am I adding? Oop, now I'm adding a negative 0.05. So I'm back to approximately 0.35. And then G of 8, I have that 0.35 plus, back to my graph, again I'm adding another negative 0.05. So I'm back to about 0.3. G of 9, I'd be at 0.3. And now I'm adding a positive 0.05. So back to 3.5, and then finally G of 10 is going to be equal to that 0.35 plus, and I'm adding another positive 0.05 there, which gives me a value of 0.4. Okay, so these accumulative areas are going to be points on my function now, right? So I just have to plot these values. So G of 0 is 0. G of 1 is about 0.3. Oops, right there. G of 2 is about 0.6. G of 3 is 0.45. G of 4 is 0.3. G of 5 is 0.35. G of 6 is 0.4. G of 7 is 0.35. G of 8 is 0.3. G of 9 is 0.35. And finally, G of 10 is 0.4. And then following the slope field, I connect my values. And it should be pretty easy to do that based on the slope field. It should kind of follow along, which it does. So there we go. That is a sketch of the graph of g of x.